Hello everyone, I'm Yang and I'm from Taiwan. I'm currently an undergraduate student in the Department of Architecture at United University. In collaboration with my thesis advisor, Professor Hong Lin, I co-authored a paper titled Impact of Urban Elevated Corridor System and Microclimate on Human Thermal Comfort, a strategies planning study for the Kaohsiung Port Waterfront, multifunctional economic and trade zone.
Our current urban environments face severe challenges with global warming and the normalization of extreme weather. Large-scale urban development has led to a significant urban heat island effect. As shown in this aerial view of the Kaohsiung Harbor area, the proliferation of high-density building development not only compresses urban ventilation corridors, but has also significantly altered and often compromised the quality of original intermediate space. This makes pedestrian thermal comfort no longer just a matter of quality of life, but a critical issue in modern urban planning. To address these challenges, this study investigates the application of urban elevated corridors as a vital intermediary system for future open space in Kaohsiung. There are three core values: ecological linkage, functioning as an extension of urban green infrastructure. It forms vertical ecological transition nodes and elevated thermal streets at ground level. Protection integration. By integrating ground level protection circulation with elevated walkway networks, it created a more efficient and safer walking system. Social catalyst is also acts as a social medium that enhances urban connectivity, promotes public interaction and leisure experiences, and revitalizes urban activity layers. Research question and analytical framework. Improvement of thermal comfort under urban heat island conditions. Can an urban elevated corridor effectively improve pedestrians' outdoor thermal comfort? Influence of design variables. What is the impact of corridor width, height, materials, and vegetation configuration on thermal comfort? Indices PET and PMV. Sustainable urban development goals. How can data-driven insights be used to implement urban cooling strategy and achieve microclimate regulation and sustainability goals? Next, through the literature review, I will introduce the key indicators and terms in this thesis. First, is PET a key index used to evaluate human thermal perception under different environmental conditions? Unlike a single area temperature value, PET comprehensively considers multiple factors, including air temperature, humidity, wind speed, and solar radiation. This index can quickly assess the effect of shading and ventilation on human thermal comfort, and it corresponds to a scale adapted to Taiwan's climate right. For example, when PET is between 26 and 30 degrees Celsius, people generally feel thermally neutral and comfortable. Assessment of pedestrian thermal comfort. Next are the PMV and PPD indices. PMV represents the average thermal sensation based on the body overall thermal balance, influenced by cycle activity, clothing, and environmental parameters. Meanwhile, PPD predicts the percentage of people likely to feel too hot or too cold, and though dissatisfied in given environment. As shown in the curve, A PMV value closer to 0 corresponds to the lower PPD, meaning higher thermal comfort. In design practice, our goal is to keep PPD below 10% to comply with an international ISO 7730 standard for thermal comfort. Analysis of urban spatial form and local climate zones. At the urban scale, building mixing and street configuration strongly affect the microclimate. Here we adopt Stewart's LCZ framework, which classifies urban area into 17 standards categories based on building height, density, and land cover. This system helps us analyze the complex mixed urban forms in Harbor City, where port facility, commercial areas, and public space overlap, providing a foundation classification for subsequent thermal environment simulations. About left area index and left area density. Finally, regarding vegetation modeling, we distinguish between LAI and LAD. LAI is defined as total one-sided leaf area per unit ground surface area, while LAD reflects the spatial distribution density of leaf in three-dimensional space per unit value. Since microclimate simulation tools such as EnviMate primarily use LAD rather than LAI for vegetation modeling, convert parameters using this integral relationship to ensure accuracy in vegetation representation within microclimate simulations. The workflow of this study begins with clarifying master plan, followed by the core patch of EnviMate modeling. In this phase, we simultaneously conduct 3 tasks: environmental parameter setting, seed model, and defining thermal comfort indices mentioned in the literature. After completing the base model, we conduct detailed corridor modeling and perform comparative analysis of 3 design variables: width to height, dimensions, material properties, and the vegetation scenarios. Finally, combining these comparative data with thermal comfort results, we derive final 3D corridor planning accommodation as a reference for urban microclimate optimization. Site description: urban development in Asia New Bay Area along Kaohsiung Harbor. This study selects the Asia New Bay Area along the Kaohsiung Harbor waterfront as a research site, with large-scale harbor development project planned over the next decade and the rapid growth of urban building complexes. Intermediate urban space has become increasingly important. This space should not only provide green areas, but also improve usability for people, which motivates this study to explore outdoor thermal comfort and optimize the future interface between the harbor and city of Kaohsiung. Master Plan Zonal Framework. This plan divides the sites into 3 main functional zones based on distance from the shoreline, created a vertically layered urban skyline. First is the front zone, an 85-meter setback area known as the Waterfront promenade. As the selected study area, it includes players, inclusive park, and recreational facilities, serving as the main interface between citizen and harbor. Next is the middle zone, centered on the Kaohsiung Software Park, forming a high-value industrial cluster. Finally, the rear zone, located inland, provides commercial, entertainment, and cultural exhibition functions. Together, this gradient of building heights from waterfront to inland preserve harbor openness and create a complete urban chain linking leisure, industry, and commerce. Site and climate analysis. This site is located in the coastal setback area of the Asia New Bay Area, along Kaohsiung Harbor. Influenced by the tropical monsoons climate, the area remains warm throughout the year, with peak solar radiation occurring in July. Sea breezes are a key climate factor, help improve air circulation and regulate temperature and humidity. However, the state also experiences strong western solar exposure. Its open and unshaded environment leads to significant heat accumulations on ground surfaces and building facades during the afternoon. Therefore, balancing sea breezes utilization with effective shading strategy is the key issue in elevated corridor planning. This study incorporates detailed meteorological baseline parameters into estimate. This included 24 hours air temperature and the relative humidity variation profiles to simulate the environmental condition during the hottest summer period. In addition, for the wind field boundary conditions, a constant wind speed of 3.0 meters per second and a wind direction of 280 degrees were specified. This study utilizes a WinMate version 5.9 for simulation analysis, and the workflow consists of 6 core modules. First, management project and space are used for project management and model construction, integrating external models from SketchUp or Rhino. Next, in simulation, meteorological parameters are configured, while library manages vegetation and material database. Finally, Biomate performs human theater conformance calculations, and Leonardo visualizes the results, producing hotspot analysis maps. Baseline material configuration for model construction. In Animate simulation setting, material properties are categorized into building material and soil substrate. For architectural volume, particularly the expression hold and surrounding buildings, materials such as a clear floor glass, aluminum, and concrete walls are used. Ground surfaces include loamy soil, asphalt road, granite pavement, and deep water. These parameters establish the baseline for thermal analysis. From the spatial model, the application of materials is illustrated. For spatial structures in the Asia New Bay Area, such as the exhibition hall, while standard buildings adopt concrete wall construction. Ground surfaces include asphalt roads, pedestrian area with granite pavement, and adjacent deep water zones. Baseline dimension configuration for corridor course section. Different corridors course sections are established as experimental variables. Heights are set at 5 meters and 8 meters, while widths include 4 meters, 6 meters, and 8 meters. Through comparison of these 6 geometric configurations, we quantitatively analyze the impact of aspect ratio on shading performance and identify optimal dimensions for improving pedestrian thermal comfort under strong solar radiation in Kaohsiung. Material configurations for the corridor roof module. For the corridor roof system, 4 representative materials are selected. PVC sound shell for lightweight shading, clear float glass, a wet roof system for ecological regulation, and a wet roof combined with a green roof system using sandy loam substrate. These materials differ in thermal conductivity and radiation transmission, combined with corridor weight variables. They enable analysis of the synergistic effect of material performance and spatial form on microclimate regulation. Vegetation model parameter settings. 3 tree forms are selected. columnar, round, and spreading. For each type, different LAI values are assigned and LAD values are defined according to vertical distribution. This parameterization simulates shading effect under different canopy densities, providing realistic vegetation input for environmental analysis. Cooling mechanism analysis. This study explored cooling mechanism from three perspectives. First, wind effect. The corridor is not aligned with prevailing northwesterly winds. Oblique wind penetration through structural gaps helps remove heat from the human body's surface to reduce perceived temperature. Second, shading. Wider green roof. Canopy block more solar radiation, reducing mean radiant temperature at pedestrian level and lowering PET. Third, vegetation regulation. High LAI vegetation improve visual comfort, and many reduce PET by approximately 1 to 2 degrees Celsius during midday peaks, collectively optimizing the thermal environment. Vegetation configuration method and planting arrangement. Various planting arrangements are tested, including single-row and double-row configurations. Crown spacing is further examined using 0 meter and 1 meter intervals. This comparison allows quantity analysis of continuous versus fragmented shading effects. Identify optimal greening layouts for pedestrian comfort. Expect outcome method and conclusion. This study completes the simulation model construction with an expected maximum PET reduction of 1 to 2 degrees Celsius. In conclusion, an elevated corridor system has been successfully developed for microclimate simulation, providing decision-making support for planning in Asia's New Bay Area. Although full simulation results are still in progress, it is confirmed that elevated corridor systems positively improve pedestrian thermal comfort in high-density urban environments. That concludes my presentation. Thank you for your attention.